Hi, welcome to the Calculus 3 assignment worksheets series. And we are in a new unit right now, and this is unit number 3. We're going to talk about in the Calculus 3. It is the multiple integrals unit. And today we are going to take a look at assignment number 1 worksheets and talk about the double integrals over rectangular regions. Okay, and in fact, this worksheet is quite simple to me. It's just kind of like the planned integrations. So we're going to pick up a few problems and take a look. Okay, so now let's go to our worksheets here. Okay, so the first two problems here is just basically is using the Riemann sum, and they choose the different sample points, right? So that will be pretty mechanical and straightforward. So the first problem I'm going to take a look, it will be the problem number 10 here. So instead of, the problem 9 and the problem 10 here, instead of just the direct integrator, they want you to take a look from the volume point, right? So from the volume of the solid, because we know when we take the double integrations, you really find the, we are trying to find the volume below that. So instead of just using integration skill, we can take a look. How about, if we look at from the, the volume points here. Okay, so for this one here, this is a 2x plus 1 dA, and the x is from 0 to 2, y is from 0 to 4. So let's first just look at what is this solid looks like, all right? So I'm going to graph here, and then I'm going to, right, so this will be my y-axis, so this is my axis, and this is my z-axis here. So of course this point is 0, 0, 0, right? Okay, so now, like when the x is from the 0 to 2, y is from the 0 to 4, so we're going to have my first, okay, so if you graph it, so this is the point, this is 2, 4, 0, right? So this is the point, and it's located at the y equal to 4 and the x equal to 2. And then in here, let's go up here, okay? So here, let me draw the pictures here. Okay, so I hope that I can draw a good picture. Not bad. I think you guys probably can see it. Okay, so here, this is the point of 0, 0, 1. See here, because the 2x plus 1, this is z, right? So this is a 2 point, so this is a 0, 0, 1. This point is 2, 4, 0. Then this point here, this will be 2, 4 what? This is a 2, 4 and the 5, right? Because 2 times 2 plus 1 is 5. This is to the y-axis is 4 at the end point. And then this endpoints here, it will be what? 2, 0, and 5, right? So basically, that's why we try to find the, this volumes here. Like I said, you can always just directly integrate this volume. But in here, we want to try to see the integration from the volume point. So in here, if you say, okay, I'm integrating this ones here, this is a 2x plus 1 dAs here, right? So you can directly see it is a combination of the two solid. So the first solid is this on the bottoms, right? So this on the bottom, this yellow ones here, I'm kind of highlight this yellow ones here. So this is the first solid we have. So what is this solid? This is a rectangular box, or you can say it's a rectangular prism. So will be the area times the height, right? So the area, the x is 2, y is 4. Then what is the height? Height is 1, right? So it's 2 times 4 times 1. Then the next thing is here, the next one, this is my other solid here. Okay, so sitting on the top of my rectangular prism. So what is this one here? This is a triangle prism, right? So the triangle prism, we know in order to find the volume will be just the 1/2 of the rectangular prism. So this is what is the base for this prism here? The base here is 2 times 4, correct? All right. And then what is the height here? The height here is z start from 1 to 5. So height is what? Height is 4, right? So you add all together, this will give you 24. So that will be the volumes, right, for this figure. So that's the same idea. So if you just physically carry out this integration, you can say this is 0 to 2, 0 to 4, and the 2x plus 1 dx dy, you will get the same things here. So that's the purpose for this problem, is just try to re-emphasize, when we do the double integrals, we are finding the volume under that curve here. So like this is the one we can draw that, and it's pretty neat, right? Okay, so then the next one's here. All this is pretty straightforward, just the integrations. And then I'm going to do another one here. Is number 38. Okay, the number 38, they say find the volume of the solid that's under the hyperbolic parabola. So it's under this curve and above the rectangles. So what is the volume here? So this one is pretty, so here this is my x range, this is my y range, right? So you have some like the some type of the curves, right? Not a curve, some type of the surface in R3s, right? Then you want to find the volume of this surface cover and also in this ranges here. So basically we say, okay, this is what we are integrating here. Okay, so now, like I said, this is 3y squared minus x squared plus 2. It doesn't matter, you integrate the dy or dx first. So let's try. So hey, I'm interested to integrate the dy first. So we say the only thing you need to be careful, if you integrate the dy, put the limit is 1 to 2, you put then the x's here. So here, the limit has to match, that's right? Okay, so that's the only thing. Then afterward, then you can just do the integration. So this is why this integration is super easy, right? So it's yx squared plus 2y. So treat what? Treat x as a constant. Then you put a 1 and the 2. Then you will get negative 1, 1. And this is 9 minus x2 and the dx. So it's a pretty straightforward integration. So the volume under that is 52 over 3. Okay. All right. So this one is pretty easy. So like I said, this section, the homework is just very routine and mechanical, but it's very easy. Okay, so now let's take a look at the last problem I'm going to do here. That will be the number 47 here. So I want to find the average value. So remember, how do we define the average value? That means you integrate and then divide by areas, right? Okay, so then they said this given rectangle, the vertices is here. So basically you need to know what is this rectangle looks like. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2. Okay, so the vertices, let's say, is negative 1 and 0. So it's here, negative 1 and 5. 1, 2, 3, 4, 5 is here. 1 and 5 is here, and 1 and 0. Okay, so this will be my R regions, right? Okay, so if this is my R regions, and I know, so X is from where to where? -1 to where? To 1. Then what is Y going to range from? 0 to 5. And then I can just find the, I can just find the integrations here, right? Okay, so also in here, so the integrations, we can do x squared y. You can integrate the dx or dy, doesn't matter, but I need to match. I'm over integrate the x, so this will be -1 to 1, and the y is 0 to 5. And so also because the x is here, so what is the area of the R here? So it's length times width, right? So it's 2 times what? 2 times 5 is 10. Okay, so then in order to find the average value, I just need to divide by 10s here, right? Okay, so now this will then become a very straightforward oh, here, I don't know why I write a y here. So y is 0 to 5 here. Okay, so it's very straightforward, just integrations here. So then this will be 3x cubed y, and then you have 1 and -1 dy. And so you have 1 over 10, 0, 5, and 2/3 y dy. Then this is really pretty easy integration. So here, this will be 1/3 y squared and 0, 5. So your final average is here. So will be 5/6. That means it's the average value over this rectangle is what? It's 5/6 here. Okay, that's it. So I said that this one is this works sheets is pretty straightforward. It's very, very mechanical, and just, try to do it. And so the over the rectangular region is pretty straightforward. Okay, that's it. Okay, so let's say, hope that this help you some. And for these sections here. So you have a good day. I'm talking to you in our next videos. All right, okay, bye.